Hello everyone, this video is a continuation of chapter 9. Mostly we'll be talking about martingales. There is a couple other concepts in here, but we're still focusing mainly on martingales. Now, before we go there, let me recall or refresh your memory. Remember that we've been using this model all along, where B0 is the option price, which was defined to be phi times S0 plus psi, okay? And this was for the one step. We have done more than one step already, but this was the main idea. Also, remember the S1, which is the stack up step 1, is defined to be S0 1 plus Kc1, where Kc1 can be either B or can be A. If we use Q instead of P, then this will be Q. This will be 1 minus Q. Okay. Also, from here, we can show that this is equals to e to the minus r delta t times f of v q plus f of a 1 minus q, or this is technically the discounted expected value with respect to q. So it's very important that we're using q of the payoff function. Now notice that the expected value with respect to q, by the way, the probability q is also what we call a measure. So the expected value with respect to the measure q of Kc1 by definition is just a times 1 minus q plus b times q, right? Because it has these two values. These are the corresponding probabilities, and this is equals to e to the r delta t minus 1. You should check this. This is a pretty good exercise where q is equals to e to the r delta t, or defined to be this. Remember, you have this on the first test anyway, so this is not should not be surprising. So therefore, if we use this result, then this implies that the expected value of with respect to q of S1 has to be the expected value of S0 of 1 plus Kc1. You can take out S0 since it's a constant, and then this will be the expected value of 1 plus Kc1. So it will be S0 times 1, because the expected value of 1 is just 1, plus the expected value of Kc1, which we did right here is supposed to be this. So it will be S0 will be 1 plus e to the r delta t minus 1, and notice that this is equals to just S0 e to the minus r delta t. I mean, it should be plus, so to the plus r delta t. So therefore, from here, this implies that S0 is equals to e to the minus r delta t times the expected value of S1 with respect to q. Now, we're going to use this result right now on our martingale problem. But notice how this is technically the definition of martingale. This is telling you that the price right now is the discounted expected price on the future, and therefore Q is going to be called a martingale measure. Now this is for a single step. The next example, we're going to do this for n steps, but this is going to be the main idea. Now, just for the record and to make things easier, notice that this means the following. The probability with respect to Q, the C1 will be equals to B. This is equals to Q. And the probability that C1 will be equals to A is going to be 1 minus Q, where Q is obviously this. And then if you do 1 minus this, you will get an expression for 1 minus Q, which you actually had to do that on the test. All right, so we're gonna now work on the exact same result as this one, but instead of one step, we're gonna have multiple steps. Now, before we go to the example, just to refresh your memory, remember that Cn is a martingale with respect to a measure, or Q martingale, if these two conditions are satisfied. Well, remember that An is technically C0, C1, all the way to Cn, or depending on which variable you have, it could be S0, S1, so it depends on the problem you have. All right, so remember we had to show two things. The first one is technically obvious, so this should be the expected value of this delta t. Notice that this part is finite, and Sn is also going to be finite because we know the expected value of that. So this should be obvious that is finite, but you still need to check this part. So this is condition 1. The one we're going to focus on is condition 2. So remember, you need to show the expected value of Cn plus 1 given An has to equals to Cn. That's what we want to show. So this is where we have expected value of Cn plus 1 given An. Remember that An in this case is S0, S1 all the way to Sn. This is equals to, and the expected value with respect to Q, all of this should be with respect to Q, of e to the minus r. This should be n plus 1 delta t times Sn plus 1 given An. Now you can take out this part because it's dependent of this one. So this will be e to the minus r n plus 1 delta t times expected value with respect to Q of Sn plus 1 given An. However, recall that Sn plus 1 is the same thing as Sn plus Sn times Cn plus 1. So therefore, this is the same thing as e to the minus r n plus 1 delta t times expected value with respect to Q of Sn plus Sn Cn plus 1 given An. Now, since this is measurable with respect to this one, you can take this part out. So you would end up with this r n plus 1 delta t, and then the Sn can go outside and it will be plus expected value with respect to Q of Sn Cn plus 1 given An. Again, this part is measurable with respect to this one, so you can take it out. This will be e to the minus r n plus 1 delta t will be Sn plus Sn, the expected value with respect to q of Kc n plus 1 given an. But remember that this is independent of an, so this will give you e to the minus r n plus 1 delta t. It's Sn plus Sn times just the expected value of q of Kc n plus 1 by independence. Okay, so since they're independent, but we already know what this is. That's what we did at the very beginning of the class. So therefore this is equals to e to the minus r n plus 1 delta t. This will be Sn plus Sn. Now this will be equals to e to the r delta t minus 1. This is what I did at the very beginning. And this simplifies to e to the minus r n delta t, because this one will cancel the 1, you will end up with this. This will cancel one of the Sn's, so this will just be Sn, which is by definition equals to Cn, so that implies it is a martingale. Okay. Which means simply the Cn, which if you look closely is just a discounted value of Sn, is a martingale. That's it. So that's a very important result. Now let's look to property 9.1. Zeta n is a martingale with respect to q, then for any j, the expected value with respect to q of zeta m plus j given am is going to be equals to zeta m. We actually used this result in one of the homework problems that we did last week. Now to make the notation easier for me, I'm just going to change this to Zn. So therefore I will write this as EQ zeta m plus j given am, and it will give you zeta m. Alright, so how do we show that that's the case? Well, the expected value with respect to q of zeta or zeta, let's just go with zeta m plus j given am. Now remember here we know that this is a martingale, so we need to use that property. What does that mean? The expected value with respect to q of this given this is equals to this. Remember that's what it means to be a martingale. So this is what we have. So then if we use the nested expectation, and this is what I said that we use in the last class, this will be equals to this. It will be zeta m plus j given am plus j minus 1. So this minus 1 is very important. Okay, given am. Now, using the definition of martingale, which we know it is, notice this part, and notice this. Okay, so if this is a one less than this one, then since this is a martingale, it should give you this part only, right? So according to this will give you the expected value with respect to q, and the highlighted part should just give you z m plus j minus 1. Okay, and then all of this is given am. So again, the highlighted, the blue part will only give you this because it is a martingale. Okay, so that's because of the martingale property, otherwise this is not the case. Right, so then you do this multiple times, then you end up with this. You should check this part. It should be z of n plus 1, which is the last time you should be able to do it, given am. And again, by using the definition of Martingale, this will just give you Zm. Okay? So we use this property in the homework, so now you can see why it works. Right, the next thing is called creating a Martingale by projection. So what does that mean? And it means the following. If you define a z or zeta n to be defined as the expected value, notice that this is now with respect to q, the expected value with respect to p of c given the filtration an, this is going to be a martingale. Okay, and this is going to be one of the homework questions, so it's pretty easy to show that that's actually the case. The book actually has the solution, so you need to read that part. But if you define Zn to be this, then this will be a martingale using the probability Tp. So it's actually easy to show this. So we need to show the expected value of the absolute value of this is finite, and also the expected value of Zn plus 1 given an is equals to Zn. For this, you just need to use the tower property that we've been using over and over, and I will show you this is the case. So this is going to be one of the homework questions. The answer is technically in the book, but you should check it out for yourselves. Now, the last thing we're going to do in this section is called the radon-nicotine derivative. But before we get to there, again, recall that Q and P are two measures, which in this case measure means probability. Q was the risk neutral measure, and P was the market probability or market measure, you can say that. And remember that this one gives you a martingale, which was the price. This one didn't give you the martingale, but both of them give you an approximation of what the price should be. And therefore these two measures are equivalent, and there is a way to connect both of them, and that's what the radon-nicotine definition is going to tell us in the next page. So now the radon-nicotine derivative, which this is only a derivative in continuous time. In discrete time is not really a derivative, it's more of a ratio. But the radon-nicotine derivative is defined as this: z of w will be q of w divided by p of w. So in essence, this is the ratio of two probabilities. So therefore, this has to be a random variable too. And z is called the radon-nicotine derivative with respect of q with respect to p. Again, in this case, it's just a ratio of two probabilities. In the continuous time, once we get there, it will be an actual derivative. So this has the following properties. Number one, the probability that z is positive is equals to 1, means always is positive. Number two, the expected value with respect to p of z is equals to 1. And 3, the expected value for any random variable c with respect to q is the same thing as the expected value with respect to p of z times z. To prove property 3 is actually pretty easy. Remember, by definition, expected value with respect to with respect to Q of Kc should be the sum of Kc omega times Q omega. That's the definition. You can always multiply anything by 1, and since these are positive probability, you're not dividing by 0, so you are allowed to do that. So this is the sum of Kc omega times Q omega over P omega times P omega. Remember that this is equals to Z, so therefore this is the summation of Kc omega Z omega times P omega, but that's the definition of the expected value with respect to P of Z times Kc. Now, why do we need to deal with this? Well, remember that Q is the Martingale measure and P is not. But if we combine the radon-nicotine derivative with the projection of Martingales we just did, then from here we have the following important result, which is this. You define Zn to be the conditional respective value with respect to P of Z given An, then this will be a martingale with respect to the probability P. Okay, so that's the important result we have here. And notice the similarity of this and what I say in the previous page or 2 pages about creating martingales by projection. Alright, so now let me just have some like final notes. I mentioned this a couple of times, but let me reiterate the whole thing. Remember, Q is called a martingale measure, and actually it's called a EMM, which means equivalent martingale measure. This means equivalent martingale measure or risk-free measure. You can say neutral instead of risk-free. So that's number 1. Number 2 says the following: if you have an equivalent martingale measure, that implies no arbitrage in the model, which is what we're trying to do. And finally, the opposite, and by opposite it means this. So if there is no arbitrage, that implies that there exists an equivalent martingale measure. For the purpose of what we're doing right now, remember we define this to have the following form, and we show that the expected value with respect to Q of Cn plus 1 given An that's equals to Cn. So this is the equivalent martingale measure, and this price, remember, we already know that this is the risk neutral measure, or there is no arbitrage if we follow this formula. Okay, so you can say this is an if and only if statement 2 and 3, and that's it. So that's why martingales are very, very important.